Thank you. Yes.
Find the down reviews.
Where do we find the sample exam? If you go where you're looking for your homework, there's a link there that just says sample exam 2. And what's that?
Are there two paper exams?
No, there are no paper exams. No paper exams. They're just that online exam. Okay, let's go ahead and get started. I spent yesterday afternoon up at the Huntsman Cancer Center with Clark. He's recovering well. He's very, very frustrated that he's having to relearn how to use his right hand. It turns out he's left-handed, so that's good. But he's still finding it frustrating that things that he could easily do before, just he's having to reprogram all of the neurons to figure things out again. He should be finding out tomorrow morning whether the tumor was cancerous or malignant or benign. But the surgeon felt that it looked benign, and so they're hopeful that they've got everything and he'll be okay. He's scheduled to come home Thursday and then go through a whole lot of physical therapy, which is miserable. Those of you that are planning to be physical therapists, whatever you do, don't tell me, or that would adversely affect your grade. Because every time I've gone to physical therapy, they're mean people. They make me hurt. Just kidding. I know you're doing it because you are filled with love. Today we have a devotional by Elder Uchtdorf. That's gotta be the best. So we'll try to get you out of here on time for that. Today I'm just going to go through question after question, problem after problem. I've tried to pick one from each topic that we've covered since the last exam, and see if we can get through all of those. Would someone be willing to give us an opening prayer before we start that, please? One last time. Thank you.
Heavenly Father, grateful for this opportunity that we have to come together one last time and review for this physics final. Please bless us that we can all be enlightened and be able to remember and recall the information that we need as we go into finals week and make decisions for future semesters and future opportunities. Please bless us with the Spirit and bless us that we can put God first in our lives so that we can have our priorities where they need to be and thus be able to accomplish the great things that you have for us. And we're grateful for Greg Francis and all that he's done for us, either both the semesters or this semester. And please bless him and his family and all the things that they stand in need of at this time, that they can feel of your love and the love that we have for him. And we say thanks in the name of Jesus Christ. Amen.
Amen. Thank you. Unfortunately, on Thursday, right at the end of class, I got really dizzy and I was about to fall down. So I called the class off 5 minutes early. It's a mistake to do that in a room with 240 pre-med students. By the time I got back to my office, there were 5 EMTs waiting to poke me and prod me and take my blood pressure and all sorts of things. So they narked on me. Before I could get back to my office, they were already waiting. Okay, let's just quickly take Roll. Okay. Get your clicker.
Yeah.
Okay. Got it?
So far.
Okay. Let's start with a simple refraction problem and I think it'd be better with the lights on. Most of the work I'm gonna do will be on the board here. We are gonna have problems dealing with all of these topics that I'm running through today, and I'm gonna run through them fairly quickly so I can get through them all. And they'll be about the same level of difficulty as what you're seeing in these sample problems. In this case, we've got a 3-meter pole, pokes up from the bottom of a pond that's 2 meters deep. The sun is 45 degrees above the horizon. What's the length of the shadow of the pole on the bottom of the pond? And so if I can just quickly draw things here. This will be the surface of the water. This will be the pole. And the bottom of the pond. Okay. Now, if we bring in a ray from the sun at 45 degrees, something like that. And this is something that you could do on your scratch paper. You don't need a special, diagram that you can draw on. You can just recreate this. And once I have the point where that ray hits the water, I then draw myself a normal, okay? And I know that that ray is going to bend towards the normal because it's going into water. And so it would go something like that. And so that means over here, it would be light. And here it would be shadow. And so we're looking for this length here. Now, the first thing I need to know is if this is 45 degrees, what is this angle in the water? Tell your neighbor really quickly how you're gonna figure that out. So we have N1 sine theta 1 is equal to N2 sine theta 2. In air, N is equal to 1. Water, N is equal to 1.33. So this is 1 times the sine of 45 degrees is equal to 1.33 times the sine of that theta in the water. If I solve that for theta in the water, I get 32 degrees. So this is gonna be 32 degrees. And now this is just a trig problem. If I call this L1 and I call this distance L2, the shadow length is gonna be L1 plus L2. And L1 is going to be 1 meter times the sine of 45 degrees. And L2 is gonna be 2 meters times the sine of 32 degrees. And that's gonna be 0.707, and that's going to equal 1.7. And so what I end up with is okay. 707, 1.07. Okay. So I end up with 1.77 meters. Something like that. Okay. I didn't write down the numbers here, but the final answer turns out to be 1.77. Questions on that problem? Yes, sir.
If you were to find like the length of the light, how would you do that?
The length of the,
So like there's the shadow and then there's like the light part. Would we have to find the length of the light or no?
no, that depends on how big the pond is. That just, everything that's not shadow is light. Okay. Let's go to the next problem. Kendra takes 3 long filament bulbs. She wraps a green acetate, that's just a plastic film, around one, a red acetate around the other, and a blue acetate around the third. While facing a screen, she uses the 3 bulbs to make a Z-shaped light source, using the green for the top, the red for the diagonal, and the blue for the bottom. Lastly, she hangs a ball of clay between her new source and the screen. What does she see on the screen? So talk to your neighbor about that. What pattern would she see on the screen? Yes. I'm sorry. Oh, you're right. Okay. So, since tangent of 45 degrees is going to equal L1 over 1 meter, I should have used tangent. Oh, my goodness, how embarrassing. Can we count that as 1 mistake instead of 2? Because 3 mistakes and you get your tuition back. That work? Okay, that's better. That's a different number than 1.77. Okay. Had you worried, didn't I? Okay. Let's label some points here. I'm gonna label this point 1 this point 2, 3, 4, 5, and 6. And figure out where each of these points end up on the screen. Well, remember, since rays go in a straight line, something that is up towards the top and to the left is going to end up towards the bottom and to the right. So it's going to end up down here. And 2 is up and to the right. It's going to end up down and to the left. 3 is going to be next to it, just like it was. 4 is down and to the left, so it's going to end up and to the right. And 5 is next to it, and we can argue that 6 will be over there. And so I'm going to get a shadow that looks like that. But this is going to be no green light. This will be no red light. And this will be no blue light. Now, where there's no shadow, I get red, green, and blue. And so that's going to be white. If we do this in a dark room, everything's going to be white except for this Z shape. Now, if I think of light as always being made up of red, green, and blue, here I've got all 3 of those, red, green, and blue. But here I've just got red and green. So what color would that be? Yellow, yeah. So that's going to be yellow. This is going to be blue and green. And that's the color cyan. And this is going to be red and blue. And that's the color magenta. Or T-Mobile. Question?
I'm super confused. Why does it flip again? I must have just missed that lecture.
If you think of a pinhole camera, if a ray is going to start up here and get through that hole, it's got to end up down here. And if a ray starts down here and gets through that hole, it has to end up there. And that's why if this is say a candle, you're going to end up with an image of the candle that's upside down. And that's the way your eye works. You get a real image that's inverted, and then your brain flips it.
We could think of it just a 180 degree.
What's that?
We could think of it as a 180 degree flip essentially.
Is the black ball blocking?
It is blocking, I'm sorry, this is going off in my ears.
She just asked.
My doctor's office. They can wait. Okay. I'm sorry, I'm giving a lecture right now. Can I call you back? Okay, thank you. Sorry. I can think of this extended source here as a bunch of a superposition of individual point sources. And each one of those is going to give me a shadow this 0.1 is gonna give me a shadow down here where just the green light is missing. It's a shadow of the green light. But the red and the blue are still getting to that point. Okay? But if I look over here at 0.2, it's giving me a shadow right here, but only of the green light. And so forth with the others. Okay?
So the reason that there's no green is because the clay ball.
Yeah, the clay ball is blocking the light that's coming from that green source. It can't bend around the source. It has to leave a shadow.
So what would happen if you got rid of the clay ball?
The whole thing would be white. Green would be just bright white. Yeah, that's a boring problem. But you'd like it to be on your exam.
So like they got to get the wires. The blue.
The blue is on the bottom with the light, and so when the light is blocked by the ball, it's the shadow of the blue that's at the top. Okay, just like the pinhole camera, the rays have to go in a straight line, and so the rays that get blocked by that ball are rays that are from the blue light going up, and so that'd be towards the top of the screen. We don't see blue for that little region, but the other light is not blocked, and so we see red and green. And when red and green combine, they are yellow. That's why we get a yellow band there. Okay. There will be a question on the exam dealing with color. Okay. And the key to those questions is thinking of color, thinking of white light as red, green, and blue. And just, you know, if I just keep asking myself, what am I going to see at this point? You know, am I going to see any red? Am I going to see any green? Am I going to see any blue? And that's the only thing you need to remember. Okay. Lens problems with more than one lens. Okay. I'm going to give you some information right now. And that is that there is going to be a problem just like this, but not with those two lenses and not with those separations. Okay. But other than that, it's just like that. I'll also tell you that the grid lines, when it got copied, are kind of fuzzy. Some of them are missing and everything, but you don't need them. Okay. All you need are those distances and the focal lengths. That's all you need, because you're not going to be drawing on the test anyway with ray diagrams. You're going to be using your equations. So let's use our equations. So the first question that you're going to be asked is, and these are the questions that are on the exam, and each one of them is worth 2 points. Okay. And we're just going to go through the questions that are going to be on the exam. What is the curvature of the light when it meets the first lens? Okay. So if we look at the light that's leaving the tip of that object, that arrow in the left, what is the curvature of that light? Well, to solve that, we just use, we first of all know that that curvature is gonna be negative because the light is spreading out. Okay, and so when it gets right here, it's spreading out from here. That's a distance of 0.24 meters. 24 centimeters. And so that's gonna be negative 1/0.24 meters. And that's going to be negative 4.17 diopters. That seem easy enough? You have your calculator there. That 1/x button is the most important button on your calculator. Okay? The next question we're going to be asked on the exam, what's the power of that first lens? Well, the power, since it's a negative lens, is going to be negative 1 over the focal length, and that's going to be negative 1 over 0.18 meters, and that's going to be negative 5.5 5 to infinity and beyond diopters. Okay, the next question that you will be asked is, what is the curvature when it leaves that first lens? Well, the one equation that you have, the lens maker equation, is whatever curvature you give the lens plus the power of the lens will be what you get out at the other side. And so that tells me that negative 4.17 diopters, that's what I gave the lens. And then I have a power of negative 5.55 diopters. And that's going to give me negative 9.725 diopters, something like that. We good? Okay, now, I'm sure you see the danger here. And that is, because I'm walking you through the problem step by step, there's a chance that if you miss the right answer to, say, the third question, all the other questions are going to be wrong. You're going to miss all the others. Now, the other option is I could just ask you the last question, where is the image going to be, and make it worth 5,000 points. I thought, giving a bunch of 2-point questions to step you through the problem was the more merciful way to go. But again, if you mix up or mess up one of the steps, you're wasting your time the rest of the way. Okay, so let's go to the next question. This is probably the most challenging. What is the curvature when it meets the second lens? Okay. Well, we know that because it's got negative curvature, this thing is spreading out from that negative lens. But spreading out from where? Well, this number tells me where the center of this circle is, which is the curvature as it's leaving the lens. That's negative 9.725 diopters. Now, if I go 1 over that, I get a radius of negative 10.3 centimeters. So that means that back here, 10.3 centimeters is where this circle appears to be centered. Now, when it gets to the second lens, it's traveled a distance between the two lenses of 27 centimeters. But it already had a center of curvature that was 10.3 centimeters behind the first lens. And so now the curvature here is gonna be, it's negative, it's spreading out. And it's gonna be 1 over this radius, which is 27 centimeters plus 10.3 centimeters. That's going to be 0.373 meters. And that gives me a curvature of negative 2.68 diopters. Now, you would expect a smaller magnitude number, because as this thing spreads out, it's part of a bigger circle. There's less curvature there. Yes, I should have used tangent, I know, I'm sorry. Okay,
Where you got, the radius?
the radius, if the radius is gonna be, 1 over the curvature, or 1 over negative 9.725 diopters, and that gives me 0.13 meters. Okay. The radius and the curvature are always 1 over each other. Okay. Now, once I have that, I'm asked, what is the power of the second lens? Well, the power of the second lens is going to be, it's a positive because it's a converging lens, 1 over the focal length of 0.21 meters. And that is going to give me a positive 8.33 diopters. Now, if I want the curvature when it leaves the second lens, well, again, if I use the lens maker equation, I take what I give that lens, I add the power of that lens, and that gives me what I get out of that lens. I gave that lens a negative 2.68 diopters. The power of the lens was 8.33 diopters. And when I add those together, I get a positive 5.65 diopters. How we doing? Okay. And again, these are the questions. I'm giving you the questions on the exam right now. The only thing that's different is the inputs. Okay. Now, the final question is, where's that image? Well, I've got a positive curvature coming out of this lens. A positive curvature is one that converges at some point. And that distance is going to be given by 1 over the curvature. And so that's going to be 1 over 5.65 diopters. And that's going to give me 0.177 meters. Okay. So what I'm going to end up with after these 2 lenses is I'm going to end up with an image of my object that is over here, and it's going to be 17.7 centimeters to the right of the second lens. And it will be real because the light coming out of the left lens is converging to a point that I could focus onto a piece of paper. No, because the way you do that without flaw is with a ray diagram, and we are not going to be doing any ray diagram.
We need to know how big the image would be.
How what?
How big the image would be?
No, because that's, you need a ray diagram. Okay. Okay, sir,
Oh, if it's inverted or. up or-
you need to know whether it's real or virtual, whether it's real or virtual.
Positive curvature coming out of the last lens, does that mean it's real?
Every time, every stinking time. Yeah, no exceptions. Okay. Because that curvature out of the left lens is telling me whether the light's coming together such that I could focus it onto a piece of paper, or whether it's spreading out as if it were coming from somewhere, but it doesn't actually come together.
Image, we have to find the distance backward.
If what?
It's virtual.
Yes, if it's a virtual image, you're gonna have a negative curvature. And when you take one over that, you'll get a negative radius. That means go back from that lens. Yeah. Okay. Again, that's gonna be 16 points on the problem, 8 parts, 2 points apiece.
Figure out if it's like an upright or lens, do we just?
It's real or-
look at it, or-
You have to draw. Yeah, you have to draw a ray diagram. Okay. I purposely chose a problem, this example and also the one on the exam, that would be very, very challenging if you were just doing the 1 over DO plus 1 over DI is equal to 1 over F, because of all the sign conventions that are just so onerous if you go that approach. If you use the curvature method, you never have to worry about anything except for, is it converging or is it diverging? That anything that is diverging is negative, anything that's converging is positive. Okay. Where's the image formed? 17.7 centimeters to the right of the second lens. Okay, there are 2 problems on the exam dealing with the eyeball. One dealing with the problem of nearsightedness and one dealing with the problem of farsightedness. Let's look at this example. A very myopic opic man has a far point of 20 centimeters. What's the far point supposed to be? Infinitely far away to Mount Timpanogos. Okay, 20 centimeters, that's pretty nearsighted. What power contact lens, when on the eye, will correct his distant vision? Assume the distance between his lens and his retina is 2 centimeters. Okay, so let's solve this problem. Okay. So first of all, the first step is to figure out what's going on in his eyeball, okay? Because you have to add some power to what he already has. And so you have to figure out what he already has before you can figure out what you've got to add to it. And so if we use the fact that the lens is supposed to focus the light 2 centimeters behind the lens, right here on the retina. And the furthest he can see is out here at 20 centimeters. Now, I know that if I put something here, he can focus that where it's supposed to go on his retina. But nothing further, nothing further. And I know that the light spreads out from this point to his lens and then gets focused down right here. So I can find the power of his eyeball by saying the K initial plus the power of the eye is equal to K final. Well, the K initial is going to be negative 1 over 0.2 meters. And the K final is going to be a positive 1 over 0.02 meters. Okay. Well, let me go over here so that it's not blocked by what's going on there. And we've got, this is going to be a negative 5 diopters plus the power of the eye is equal to a positive 50 diopters. And so if I bring this negative 5 over, what we find is that the power of the eye is equal to a positive 55 diopter. Okay. Now, what do we want it to be? Well, we want her to see light from infinity. We want her to have that light focus on the retina back here. Okay, so this would be the power of the contact plus the power of the eye. That would be combined P total. Okay. And so if I do K initial plus P total, I still want that to focus at 2 centimeters. And so I still want that to be a plus 50 diopters. Well, if this light is coming in from infinity, 1 over infinity is 0. And so that means I want the total power to be 50 diopters. And so if I want this to be a plus 50 diopters, and the eye has a plus 50.5 diopters, I'm sorry, 55. Then I would like the P of the contact to be equal to negative 5 diopters. And we knew that since this person was, this man was nearsighted, it was going to take a negative lens, a diverging lens, to make this happen. And you can tell that this is a diverging lens because it's thinner in the middle than it is on the ends. Okay, a converging lens is always fatter in the middle. Do a quick check on your neighbor. Okay. There are 2 questions on the exam dealing with polarization. And the the only thing you need to know about polarization is that if you start with unpolarized light, going through the first polarizer gives you half out the other side. And the second thing you need to know is that if you start with polarized light, you get this cosine squared law. And so these polarization questions are more math questions. And you'll notice that it's cosine, not tangent. I'm never gonna live that down, am I? That's okay, at least it happened on the last day. Okay. So. If I divide this equation by I0, I get cosine squared theta. And we would like to have the polarized light that's polarized along the y-axis. We would like only 30% of it to get through. And so I would like this ratio to be 0.3. And so now you see that this is just a simple math problem. I want cosine of that angle. If I take the square root of both sides, to be square root of 0.3, square root of 0.3. Okay. And so that means that theta is going to be the inverse cosine of the square root of 0.3. And that turns out to be 56.8 degrees. I mean, that's going to be easy. That's the kind of question you're going to be grateful for to, you know, be a sure thing.
So this means that says 0.3 times the original intensity, but that means the original intensity of polarized light.
Of the polarized light. This equation only deals with, this is what came in the backside of that polarizer and what comes out the front side. Okay, just that one interaction. Okay. Well, that was quick. Thin films. Let's talk about thin films here. Two flat pieces of glass having n equal 1.55 are smeared with cooking oil with a index of 1.47 and then pressed tightly together. When the glass oil sandwich is illuminated with yellow laser light of wavelength 580 nanometers, a pattern of light and dark circles can be seen in the light reflected from the front surface of the glass. In the picture shown below, the dark region at the center of the pattern is present because the oil thickness there is much smaller than the wavelength of the light, much smaller than the wavelength of the light in oil. Find the thickness of the oil at the first dark ring here. Now, the reason that center is dark when there is no path difference, no significant path difference between the light that hits the top of the oil and the light that hits the bottom of the oil, is because there's a phase transition, there's a flippage, okay? When I go from, let me, if I go from glass to oil, I'm going from, essentially, I'm going from slow to fast. And there's no inversion, there's no flippage. But when I go from oil to glass, there is a flippage. So if I look at a ray, remember, you want to figure out what your film is, and in this case, it's oil. And so you look at a ray that bounces off the top layer boundary with the oil, and one that bounces off the bottom boundary of the oil, okay? And because I don't have any inversion here, but I do here, pow, okay? That's why I have a dark spot when my T is equal to 0, because I already have that 1/2 wavelength from the inversion that would put these two rays that are coming to your eyeball out of phase, out of step. Okay. Now, that means that for destructive interference, I want 2T to be equal to M lambda N. Tell your neighbor why that would be the equation that I would want to use.
That makes sense.
Okay. If these two rays, the blue one and the red one, oh, that's not red. The other red. And both of these rays are yellow in color. If both of those are in step, then I'm going to get constructive interference. And if I move this one over one wavelength, I still get constructive interference. But if the blue one has this phase shift, well, when it's reflected off, all the crests become troughs and all the troughs become crests. And now, even though I've shifted by one wavelength, because of that extra half wavelength due to the inversion, I'm out of phase. I have destructive interference. I get a dark ring. And so the first ring is going to be for M equal 1. So I just solve for the thickness, and that's going to be lambda over 2. And you remember that lambda N is just lambda in the air divided by the N of the oil. And so that's going to be this. So that's going to be 580 nanometers divided by 2 times the 1.47 of the oil. And that's going to give me 197 nanometers. And so the answer would be D. Okay. Yes.
Why was your M1?
Oh, each one of those rings is associated with another M. What we see is that we're told that the thickness at the center dark spot is negligible. And so clearly what's happening here is the oil's getting thicker and thicker as we go out. And so the first ring would be M equal 1, second one would be M equal 2, third one M equal 3.
Why wouldn't we use the M plus 1/2?
What's that?
Wouldn't we use the M plus 1/2?
Oh, because we're looking for destructive interference. And we've already got a half from this inversion right here. If my path length difference is an integer number of wavelengths, and it has to be the wavelengths in the oil, that would give me a bright spot if there wasn't an inversion. But there is an inversion. And so that's, remember, we have these two formulas. You've got the 2t is equal to m lambda n, and 2t is equal to m plus a half lambda n. And you need to figure out when to use which equation based on whether there's an inversion or not.
So the n, does it go from like 0, 1, and 2? So if you were to hypothetically look for the following rate, would that be m equals 2 or m equals 3?
M equal 2. Yes. And m equals 0 is this one here. M equal 1, m equal 2, m equal 3, m equal 4, m equal 5.
How do you know if you're trying to find destructive or constructive?
They told you it's a dark ring. Destructive interference is where the light cancels out and you get no reflection. So the bright spots are constructive, the dark are destructive.
Okay, so if we were trying to find the first light ring,
Then I'd use the one with the half in there.
okay.
Yeah.
Can you explain why there's a phase shift at the bottom of the oil film?
Yes, when you go, really quick, how many of you had 105 from me? Okay. So you are in the advantage on these problems because we studied what happened when a wave hit a boundary. And when it was going from a slow to a fast medium, the reflection came back without any phase shift, without any inversion. Crest went in, crest came out. But when we came from a fast to a slow medium, it was like we were hitting a brick wall, like we were hitting a fixed end. And then a crest went in, but a trough came out, okay? And so here, I'm going from n equal 1.55 to n equal 1.47. The smaller the n, the faster the wave, okay? So here I'm going from slow to fast on the red one and no inversion. Here at the bottom of the oil, I'm going from 1.47 to 1.55. That's fast to slow. That's the fixed end where it gets inverted.
And why don't you need to account for the reflection off the glass at all?
Why don't I,
Off the top end of the glass and
on the top?
and the bottom end of the glass, yeah.
Oh, I'm not looking at the reflection off of this surface. I'm looking at the reflection off of the oil top and the oil bottom. Okay, there is some reflection off of this glass, but it's going to be the same for both. And that's,
So you can just neglect it.
I don't have to
Neglect it, okay.
concern myself with that. Yeah, figure out what your film is and then,
So with the homework we were going through, the tutorial, we had a situation where the light was transmitted.
what's that?
In the tutorial, we had like the light being transmitted. We used to box information around steel structure.
Yes, I can.
I guess that's what I'm wondering why.
So in the tutorial, we had this this soap film that was changing its thickness because of gravity and getting thicker as it went down. And we calculated the wavelength of that light that we were using in air, and we got 400 nanometers, okay? And the soap had an index of refraction of 1.33. Well, the wavelength in the, that should say soap, I apologize, in the soap is 300 nanometers, okay? Now, there's the picture that you had. And what we found in the tutorial, not the homework, but the tutorial, was that when I had my path length difference, which is 2t, when that was half a wavelength, I got a bright spot, a bright reflection. And that's because as I go from air to soap, I've got an inversion. That's fast to slow. But on the back, I don't have an inversion. And so I would use for my bright spot this equation here. Now, on the other side, the light that goes through, there's no inversions, okay? Neither surface had an inversion. And so there we use the other formula. And so we found that this one gave me a dark spot. And then if I go down a little bit further where it's a little bit thicker, where my path length difference is one whole wavelength, well, on this side, the reflected side, I've got that inversion, and so one whole wavelength, and then I add the inversion is going to give me destructive interference, or a dark band. But on the other side, because I don't have any inversion, I get a bright band. So energy is conserved. If it doesn't reflect back, it goes through. And if it does reflect back, it doesn't go through. The next bright spot we found was 3/2 wavelengths for the path length difference, plus the inversion gave me an integer number or bright spot. And that was a dark spot for, in your homework, for the transmission. And then the next dark spot was 2 full wavelengths, and that was a bright spot for transmission. Okay? Now the formula we were using for bright spots over here had the 1/2 in it to compensate for the phase inversion. Ultimately, I want these two waves to be in step when they come to my eyeball. If I've got this half a wavelength due to the inversion, I have to take that into account with my path length difference so that I get them back in step. And so this would be the m = 0 bright spot, the m = 1 bright spot, the m = 2 bright spot. For the transmitted light without any inversion, I use the other formula. And so you see that whereas this formula would give me a dark spot for this wavelength or this thickness, it gives me a bright spot for transmission. And so energy is conserved. That answer your question?
Yeah.
Okay. Oh boy. Elder Uchtdorf, I'm hurrying. I promise. Okay, let's go back to our questions. Photoelectric effect. Okay. The photoelectric effect, everything can pretty much be solved like you balance your checkbook. Okay, the kinetic energy that the most energetic electrons that come off are just equal to the energy of the photon that's given to the electron minus the work function. This is how much energy it takes to escape from the metal. If the photon gives the electron this much energy, and it had to use this much energy to escape the metal, the energy that's left over is going to be kinetic energy, racing it up to the collecting plate. Now, this is just the work function is the energy required for electrons at the very surface. This is the minimum amount of energy that it's going to take to escape. And so those will be the maximum, the fastest electrons that come zipping off of that surface. Okay, but this is just bookkeeping. And then we know that the E photon is Planck's constant times the frequency, but we always write it in terms of the wavelength. And this is the most important number that you'll need to remember, 1240 eV times nanometer over the wavelength, okay? Now, this work function, that's given when, if I find out the minimum, how much, let's see how to say it, the longest wavelength that'll still pop out an electron, okay? The longest wavelength is going to give this to me, so that is going to be 1240 eV nanometers times the maximum wavelength. Okay. So in this problem, we have a wavelength of 70 nanometers. And so that's going to give me 17.7 eV. And so we know that Ke max is going to be this 17.7 eV minus the work function. In this case, we're given the work function is 4.82 eV, and that's going to give me a total of 12.9 eV. Now, it turns out in this problem, they actually want to know how fast these maximum velocity electrons are traveling in meters per second. And so I have to convert EVs into joules. And that's going to be 2.06 times 10 to the minus 18 joules. Okay, and the conversion factor, of course, is the charge on an electron, 1.6 times 10 to the minus 19. So now if I use the fact that kinetic energy is equal to 1/2 mv squared, that gives me V is equal to the square root of 2 kinetic energy over m, and I get a number of 2.13 times 10 to the 6th meters per second. Okay. Yes.
Can you move the whiteboard up a little bit so we can see?
Yes.
How you converted it.
1 eV is equal to 1.6 times 10 to the minus 19.
Where did the 2.06 times 10 to the 18th joules come from, and where'd you get the
Uh,
maths?
I said that, 1 joule is equal to, um, 1 EV is equal to 1.6 times 10 to the minus 19 joules. And that gives me 2.06 times 10 to the 18.
Where'd you get the maths?
The what? Where did I get the 1.6 times?
Math.
I think it's on the equation sheet.
Oh, the mass,
For an electron.
the mass, it's a mass of an electron. Everyone knows that. Right? They all have that mass. Question? Nope, okay. We are running out of time, so let's just look at the half-life problem. The radon gas has a half-life of 3.83 days. If I start with 8 grams of radon gas at time t equals 0, what mass of radon will remain after 2.5 days? Again, with half-life problems, you only need 2 equations. You need this m value, which is just how many half-lives you have. And then this formula here will tell you what you have left after that many half-lives. So in this case, we say that the m is 2.5 days over the half-life of 3.83 days. And that's going to give me 0.653. That's how many half-lives have expired or have transpired. And that tells me that n over n0 is equal to, let's do it this way. N is equal to n0 over 2 to the 0.653 power. And that's going to give me 5.09 grams. The N0 was 8 grams. Okay, it is about time to go to listen to Elder Uchtdorf. Before you go, I just want to do one more clicker question quickly. Which problems are hardest for you? Okay. Last call. Okay, thin films win. Okay. Good luck, people. I love you, people. Oh, I would give it to you if you needed it.